one of the questions that Dynamic Ratings often gets from our customers is, we get calls from customers basically saying, either they've experienced bushing failures or they're experiencing gassing in some of the GSUs in their renewable installations with the inverter-based generation. So, it just prompted me to maybe dig in a little deeper and, hence the topics of this webinar. So to begin with, the first thing I wanted to look at was, is there any truth? Are we seeing higher failure rates in renewable applications versus our traditional applications? And unfortunately, this data here is from the CGRE Technical Bulletin 939, and which was completed in 2024, so it's relatively recent. And unfortunately, even CGRE recognizes that they really don't have good data that focuses just on renewable applications when it comes to those generator step-ups and stuff. So the data that we're looking at here is basically all transformers. So this could be just a standard distribution transformer, a transmission-based transformer, or it could be a generator step-up. So, but what we're seeing is the failure modes, regardless of the application, the percentages change, but the overall methods don't, or that, the modes don't change. So here we're seeing, electrical is a big piece of this. Electrical failures, dielectric failures, mechanical failures, things like that. When I talk mechanical, pretty much you're talking more on the through fault side of things. What's happening, and obviously those types of failures are probably more prominent on the distribution side, maybe a little bit on the transmission side, but less when it comes to the transmission based or the generator step up based assets. So when we break this down into break this apart a little bit, traditional substation transformers, you can see those and GSUs are pretty much the same. Now, again, unfortunately, our renewables are mixed up in here. And the generator step-ups and renewable applications, I think in general, most industry experts really believe that we're seeing increased failure modes when it comes to those assets. But unfortunately, there's just hasn't been enough of a focus on people reporting that, hey, this was in a renewable application, and maybe we need to treat this separately or categorize it differently. But ignoring shunt reactors, you can see both the substation transformers as well as the GSU transformers. Basically, they have similar failure modes. Dielectric is a big issue. Electrical is going to be a big issue, and I'm going to cover basically what we expect to happen as we introduce more renewables and how these failure modes might change. So to begin with, when we look at the factors contributing to these transformer failures, basically, one of the big ones that we talked about is insulation breakdown. Our previous speaker talked a little bit about some of the tests you can start to identify, insulation breakdown. We're going to focus more on online characteristics and how this can impact it. Of course, moisture was one of the things that he addressed at the end of his presentation. Moisture, again, can have a significant impact on the thermal aging of the transformer and greatly shorten that life. What people probably don't recognize is when you have load and temperature fluctuations, as you have that expansion and contraction of the oil, whether it's in the transformer or in the bushing and stuff like that, that's always a possibility for moisture ingress to increase on that transformer. As we go through those temperature and load fluctuations, basically the oil is expanding and contracting. As that's occurring, we may be pushing dry air or nitrogen out of that transformer, and then giving an opportunity to suck in moist air. So, of course, when it comes to overloading and thermal aging and things like that, overloads are going to have a significant impact. So if we're overloading our transformer and not managing our cooling properly, any type of thermal condition is going to cause increased thermal aging. Harmonics is probably the piece that people don't focus on enough when it comes to the renewable applications. Back in my early career, I heard a lot about transformer failures, but this was more in high-rise apartments and office buildings and things like that. And they're focusing more on like the third harmonics and things like that, and the impact that they're seeing with wiring burning up and stuff like that. Harmonics can have a significant impact on the thermal aging of that insulation. And I'm going to cover that in more details because ironically, that harmonic profile that we're seeing from the renewables has shifted and has changed over time, and that can have a significant impact. But probably the one thing that people recognize the most in these renewable applications are the load and temperature fluctuations that we're seeing. And I'll cover, how we're gonna, or the impact that that can have on the assets. So this happens to be a load profile from a solar farm where we installed some monitoring equipment to help them. And some of the things that I noticed here initially, so the blue, red, and the green traces are basically the voltage this is on the secondary side of the transformer. And you can see for the most part, at this part on the left-hand side here, they fluctuate a little bit, but they're pretty steady state, and they at least are moving as a group. What I think is interesting, that's the period when it's, basically where we're generating, here we're generating about 100, 110 megawatts. This is the VAR flow coming from the inverters at that point in time. What's interesting is how this shifts and how drastically it shifts when they're taking it offline, and here's when they're bringing it online. But when they're taking it offline, we can see that megavar output greatly increasing from basically 0 megawatts, almost a unity power factor, to getting up here where we're producing, 60 megavars. You can see our megawatt flow is pretty much staying the same. So at that point in time, I mean, when we see that, because we know VARs can have a significant impact on voltage, that's when we start seeing, significant changes in our voltage profile here. And we're going to see that in some of the online monitoring data. But these rapid changes in this voltage that we're seeing here do cause additional stress on the insulation. And of course, as they actually finally ramp it back down, eventually things when we're offline here at this point in time, things are nice and stable. So, this type of load profile and things like that, you can see just how, the impact, we could be looking at some harmonic resonance on the system. We could be looking at just the VAR contribution. And it could even be how they're regulating or how they've been asked to regulate based on the ISO for the wind and solar farms. But again, it's, things are, that the fast ramping of these renewable assets can create some havoc when it comes to the insulation in our transformers. And it can also impact our switchgear and stuff like that. In this case, it's not uncommon. I mean, for solar farms, wind farms, I mean, you could have fast megawatt ramps of up to, 50 megawatts per minute. So, I mean, they could be coming on very, very quickly, and that's going to stress our insulation. Now, that's only where it starts. So we talked about the voltage profile and things like that. We'll get into a little bit, but here we're also talking the harmonic impact and the impact that the harmonics can have on that insulation. So here we're looking at the total harmonic distortion. This is the total harmonic voltage distortion. And, IEEE, IEC are pretty much recommending, about a 5% maximum total harmonic distortion. So, but here we're looking at when we get into the maximums, for the averages, we're pretty much, we're close to that. But this is about a 10-minute average. But when we start looking at the 3-minute averages and things like that, or 3 minutes max values, basically we see our harmonic distortion increases quite a bit. We're approaching values of about 8%. Now, what's ironic or what's really interesting is that just happened to be one snapshot on the waveforms. But what I did is I would look through the history, and this monitor, power quality monitor, happened to be installed for about 3 days. So I looked over the entire duration, and we could see here we're hitting maximum voltage distortions, about 7 approaching 8% here. The current distortion is where I thought was really interesting, is 8.5, or 11.5, 11.4. So I mean, we're exceeding 11% total harmonic distortion when it comes to the current. And again, those IEC and IEEE limits are about 5%. So again, anytime we've got harmonics on that system, that can introduce additional aging on our insulation. Now, one thing I talked about, like I said, early in my career, we always focused on basically what they called the triplet harmonics, the thirds, the ninths, those types of things. And when there was a lot of like 6-pulse drives out there, so we saw a lot of 5th and 7th harmonics associated with that. And we do see that here, but in a lot of renewable applications, we also see a lot of higher order harmonics. Here we're looking at basically, the predominant component in the harmonics is a 17th harmonic. And when you look at the C-grade bulletin on asset reliability and stuff, they're pretty much recommending that you need to monitor harmonics because we could be seeing harmonics out to the 50th when it comes to these renewable applications. And of course, as you increase the harmonic here, the frequency of that harmonic is increasing. So the thermal stress and the aging stress associated with those harmonics is going to increase. So again, as when compared to renewable applications or traditional applications, the transformers in these renewable applications and really data centers fall into the same category. They're being stressed. They're seeing a lot more impact from harmonics than historically what we have seen in the past. Now, a little bit later, I'm going to also talk, I think everybody's pretty aware of the effect that harmonics can have on aging and thermal, the thermal process, the temperatures within the transformer. But that's not the only problem that we're worried about. Harmonics can also impact partial discharge and things like that. And that's a piece that's very, very interesting. That was the current distortion here. Here's the voltage distortion. And again, we talked about that earlier. We're seeing values exceeding 7%. So in addition to that insulation breakdown that we're worried about when it comes to renewables, we're also concerned about dielectric failures. And this is the area where we often get questions from customers because they're seeing increased DGA values. In particular, they're seeing high levels of hydrogen. And typically those are being associated with partial discharges within the transformer. It could also be due to transients and overvoltages, switching activity between the vacuum breakers as they're taking the wind turbines and the inverters online and offline. There's a lot of transients and overvoltages there that again could result in dielectric failures within our transformers. And of course, anytime we have those partial discharge transients like that, basically we could be driving changes in power factor and capacitance, not only in our bushings, but also could affect the power factor and capacitance in our the main insulation in the transformer as well. Now, transients and overvoltages is one thing that I was a little bit surprised. It's actually quite interesting. Here's a traditional switching transient for a machine-based or rotating machine-based generation. And because of the inertia and the momentum, it resulted in a pretty stiff system. And if we had a switching transient with machine-based generation, basically what you're looking at, typically you'd max out at about 1.2 per unit when it came to the voltage. But what's interesting here is look at the frequency of that transient. Now, yes, there's maybe a high frequency component, but it was pretty short-lived. But then the remaining of it was basically followed that 60 hertz pattern typically. So basically, it was sort of short duration, and so it followed again. The frequency of that transient was much less than what we're seeing with the inverter base. With the inverter base, we're seeing much steeper wavefronts, much higher per unit values when it comes to those switching transients. So here we're exceeding 1.3 per unit. And basically the frequency is what's really surprising me because you're not hitting that insulation with that transient one time, you're hitting multiple times over the course of a very short duration. Of course, when we look at the windings in a transformer, basically what we're looking at here is an inductor. So what happens when I hit it with that high frequency transient here, inductors, of course, resist instantaneous changes. And because of that, what's going to happen is the stress of that switching transient in that application is going to be pretty much localized to the first few turns in the transformer. So that's why when they look at renewable, failures on renewable applications, typically it's going to be the first few turns of the winding that are going to experience that problem. Because all of those, when they have those switching transients, basically all of that stress is going to be, isolated to those first few turns. Where if we have machine-based, basically it's not only lower voltage, but it's also because of frequency, it's going to affect, maybe a greater portion of that winding. So again, the stress when it comes to those inverter-based, when we have switching transients and things like that, which are occurring every day as we bring these resources online and offline. And not even to say when they have failures and things like that. But the stress that these switching transients put on the windings has, and bushings as well, has a significant impact on the increased failure modes that we're seeing. In addition to that, we sort of talked about it before, but there can be a lot of voltage fluctuations when it comes to the inverter-based generation. Again, the inverter-based, basically it's a reactionary system. It's not relying on momentum, it's relying on just reacting to what it's seeing on the system and trying to compensate for that, whether it's increased, if there's an event on the system, a fault on the system or something like that, that inverter is going to react and basically start pumping VARs onto the system and stuff like that. Now, what I thought was interesting here for the voltage fluctuations, and again, this is that same power quality report that I was looking at before, but basically within a very short period of time, these almost have the same time signature here. We're about, 350 milliseconds apart. And I went from a positive 2 kV to a negative 2 kV in a very, very quick period of time. So again, we're seeing very short duration, very fast, fast changes in voltage, fast switching transients and things like that, all of which can impact that insulation and drive the partial discharge failures, result in partial discharge, and basically increase that stress. So really, when it comes to the GSUs, typically what we're seeing or in these applications is, we're seeing more increase, we're seeing the thermal issues, but it's really the hydrogen and stuff that we're seeing in those applications are really due to the partial discharge activity and possibly, what's happening with the transients and overvoltages during that switching activity. Whereas with traditional machine-based generation and stuff like that, with those, we may have some thermal, but no, for the most part, that transformer size pretty close to the generator, but we might see basically more mechanical interaction if there was faults on the system and stuff like that. So, so the next part, we talked about partial discharge, the impact that partial discharge can have on the insulation. Of course, partial discharge is basically one of the leading causes of insulation breakdown. And typically what we're looking at with partial discharge is it tends to occur as the true partial discharge, if I'm looking at a void in the insulation, occurs basically as the voltage stress is increasing on the sine wave. So it's between 0 and 45 degrees here, and from 180 to 2.25 here. And then you can see after that, basically at that point in time, that impulse or the pulses associated with are going to start to decrease. So they tend to be at a minimum at our 90 and stuff like that, or extinguished at that point. So what we're seeing basically here, again, as that voltage stress is increasing, that's when we're seeing that insulation spark over. And the reason being is the void in the insulation has a lower dielectric than the insulation surrounding it. Now, what happens as we introduce harmonics, basically, we're going to start to see increased partial discharge activity. We're going to have more voltage peaks, which can trigger additional discharge voltages or additional discharges. We're also going to see changes in the inception voltage. It's going to start occurring earlier, and it's going to start basically ending later. So the duration of the partial discharge event is going to increase. Ultimately, that's going to result in, because of the increase, if we have when we look at the transients, because the voltage gradient is steeper, it's also going to result in higher dielectric stress. There's going to be more energy because there's more pressure behind it, which is going to drive, again, increase the insulation aging. So in the end, basically all this is going to result in increased partial discharge is going to increase, and it's going to result in, or it's going to increase the level of insulation degradation that we're seeing. The other thing that can happen as we introduce partial harmonics with partial discharge is because now I may have more partial discharges. I could see overlapping patterns and things like that. So the diagnostics actually could become more difficult. Now, give you a rough idea on the harmonics that we're looking at, that 17th harmonic that I was looking at before. So here what I did is I overlaid what the harmonics would look like on the fundamental. So we can, and basically what we're seeing here is each one of these, the oscillation of that harmonic could, if it's high enough, could result in partial discharge. So instead of just one partial discharge here and one on the other side of the sine wave, basically I'm looking at multiple within that same cycle. So again, you can see how this can result in increased partial discharge frequencies. The other thing that happens is with the expansion and contraction that we talked about. Basically, as we're adding load, we're driving the temperatures up, and it's increasing, the oil expands, and we're increasing and decreasing the pressure within, both the transformer and within the bushing. As the temperature increases, the oil expands, and that also has an impact on the partial discharge activity. So this was some research that was done by BC Hydro. And what they had was they had some degraded bushings that they put in the lab. And what they did is they increased the pressure within that bushing. They wanted to see how it performed, how the partial discharge behaved. What we're seeing is when the pressure is high, basically at elevated loads, partial discharge activity, the picocoulombs of that discharge are actually relatively small. But if they go back to 0 psi, basically we can see we've got much higher picocoulomb values. So again, the higher the picocoulomb, the greater the discharge, and that could degrade our insulation. So it doesn't appear, obviously, there must be some other factors here, because here we've got one where it increases and then it later decreases. But in general, the overall results of their analysis was that partial discharge, there's a direct correlation typically between partial discharge and pressure. So that, again, as we go through that thermal cycling on those units, is going to have an impact on the partial discharge. When pressure's up, we're not going to see it. But when it comes offline, especially if you have rapid cooling and things like that, if we're cooling down very quickly, we can expect to see increased partial discharges on those units. The other thing that they noticed is basically when we introduce pressure, I already talked that harmonics can impact, basically the when PD starts and when it extinguishes. Basically, oil pressure can do the same thing here. So here we're looking at, out at 7 psi. Basically, I'm looking at that top curve here. My partial discharge is going to extinguish at 50 kV, meaning that, if it's starting here, basically it's going to once it starts, basically it's going to extinguish at some point in time. So we're looking at some place, the upper part of that sine wave. Whereas at lower pressures, basically it's going to continue for a longer duration. So it's going to start sooner and later. So the duration of that partial discharge activity is going to increase, which again is going to increase the insulation degradation, and both in the, in our bushings as well as in our transformer. So, so now we're talking, factors that affect insulation breakdown, dielectric failures, things like that. Mechanical faults can be a concern, especially with distribution transformers, transmission-based assets, things like that. Through faults are typically one of the leading causes of failures in those. With GSUs, typically, as we saw in the first few slides, it's not as great of a concern. But if we look at traditional generators, we have limited exposure to faults. We don't see a lot of faults with those. They tend to be high magnitude, but fairly short duration, lower frequency, but they can be a significant mechanical impact. So, I mean, there are a lot of forces behind there. So we typically see it's more of a mechanical nature when it comes to those rotating machine-based assets. With inverter-based, basically the fault currents tend to be lower. The inverter outputs are current limited. So because of that, we're not as worried about, the levels of the faults, because again, we have that current limiting. It could be high if you have if it's in an area of the grid that has a high fault duty, but the generation itself isn't going to basically supply a lot of fault current because of that current limiting capacity of the inverters. What can happen though is increased, there can be a significant increase in the number of faults that the transformer is going to see or the GSU is going to see. And as we increase it, there could still be basically a cumulative effect of those faults on the transformer itself. So whereas the dielectric stresses, when it comes to inverter-based transformers and inverter-based applications, basically a dielectric stress due to transients, over voltages, partial discharges, things like that are going to pose a much greater threat than what the mechanical forces do in inverter-based generation. The other thing that happens is basically with inverter-based generation is, again, it's a very reactionary system. So if I have a fault on the system, it's not uncommon basically to start injecting high levels of reactive current to try to keep the voltage up during that fault. Of course, when the fault subsides, if we're still producing that high reactive, a lot of VARs on the system, that can result in basically short-term voltage spikes and things like that on the system, which could distress our insulation. The other thing is it could cause asymmetric flux within the core of the transformer, which again, is going to start to stress the transformer in different ways. There could also be temporary overexcitation conditions, due to changes or frequency variations and over voltages, under voltages, as the inverters react to system conditions. So, when we see this, there can also be increased straight flux heating. It can drive localized core saturation, which can drive vibration and things like that, all of which are not good for the insulation in general. So when we're looking at that, that can also degrade the insulation. So again, the key component here is, unlike synchronous machines, the inverter-based reactors, basically, they're injecting reactive current, they're responding to the events and stuff like that. Now, this may not be, some of this depends on what the requirements are for the ISO, because if we look at, the fault on the Iberian Peninsula or the blackouts in that situation, there they had a little different situation. There, they basically required them to put out the power that they're producing basically had to be at unity power factor. So they're power factor limited. So when they started to experience faults on the system and voltage deviations and things like that, normally you would expect the inverter-based generation to try to react to keep that voltage up. In that situation, it's actually a pretty interesting study that they did. The inverters basically were not able to start producing those VARs to help keep the system online. So actually the VAR starvation that started to occur on the system led to additional voltage fluctuations, like frequency variances and things like that, which led to some of that collapse. Really wasn't a function of the inverter-based system. It was more some of the rules and regulations that the system operators had put in place as to how they were supposed to respond. So what do we do about all this? So if you go back to the initial, failure modes that we have and the components that are failing on our transformers, we can start to apply basically the monitoring technologies that can be used to help protect those assets. So in this situation, basically, if we're talking bushings, basically, we can monitor the temperature of the bushings, infrared, things like that, make sure that we're not overheating that way. We can do bushing monitoring. Basically, online bushing monitoring is a very, very effective technology to help identify degraded bushings. Works on pretty much any bushing type, whether it's the newer RIP and RIS bushings or the older RIP or OIP or the resin bonded paper. Partial discharges, basically, as we talked about earlier, partial discharges in the presence of harmonics and pressure changes and things like that, we do expect to see increase in partial discharge activity. And of course, monitoring harmonics, we've talked about. When it comes to the main tank, the windings and stuff like that, it's really not that much different. We're talking temperature. Of course, DGA is pretty much common, whether you're doing key gas or a multi-gas monitor. Putting some type of DGA monitoring on the transformers themselves is, pretty much almost a guarantee. Most manufacturers or most renewable providers are putting some type of online DGA on those transformers to identify, increased gassing and just, fairly cheap insurance. Moisture and paper, we talked about that, the expansion and contraction that we're seeing due to the thermal cycling, basically, can result in increased moisture ingress. As I have increased moisture ingress, the chances of the risk due to bubble evolution increase as well. So, it's good to monitor not only the moisture in paper, but also to identify if the thermal elements, are we loading the transformer in such a way that we could be driving that moisture out and possibly creating bubbles in the oil, which could result in a dielectric failure within there. Of course, partial discharge for the main tank is significant, we spoke about the benefits of that before. And then, lastly, since faults can be a significant problem, monitoring through fault activity on the transformer can give us an indication of mechanical health, but then also the harmonics that are present on that system. When it comes to the leads, basically we're looking at the same thing that happens with the windings. Tap changers are those other technologies. Most GSUs don't really have a tap changer. So, how often this applies to renewables, but, if you do have a tap changer, there's definitely monitoring in place that can do that. And when it comes to generation activities, GIC may or may not be an issue for you. It really depends on the length of the transmission lines and stuff like that. So if we look at that, when we look at those monitoring technologies, some type of online DGA is pretty much always recommended. At a minimum, you're going to want a key gas monitor doing hydrogen or possibly hydrogen and carbon monoxide. There's also some monitors, basically key gas can do hydrogen, acetylene, and carbon monoxide as well, in addition to the moisture. Many renewable providers are focusing more on the multi-gas monitors, so they can get additional information and basically better assess in real time and what's happening on their transformers. Now, how is this used? This is a case study that we had, and basically in this situation, we had a bushing lead failure. And so here they had a dynamic ratings partial discharge monitor on the unit, and you can see the partial discharge intensity values are very, very low, and were low for a long period of time, when suddenly we saw a very large spike basically on one phase, channel 3. So at this point, the monitor was in alarm. The customer called for support and basically said, "Hey, what's going on?" Definitely we felt that it was new. What I thought was interesting though was, it came, but it also went very quickly, but it definitely deserves some attention. Now, what's ironic here is, you notice this happened somewhere on July 9th, basically, mid-evening and that type of thing. Here's the DGA monitor. If we're looking at the DGA monitor, basically this is almost a day later. So it's almost like a cause and effect thing, where we basically had a problem. Partial discharge monitor identified a significant increase in energy. And then, almost a day later, about 20 hours later, basically we saw an increase, or the DGA monitor went into alarm at that point in time. What's interesting, here we did have an increase in hydrogen, but I'd say that was a fairly moderate increase. If I'm tracking, the trends and stuff like that, I may have gotten alarmed depending on how sensitive I was setting this, but it's really some of the other gases that were causing this, the methanes, the ethylenes, and things like that. So if we look at that and we do an analysis on that, basically, looking at it in the Duval triangle, basically here we had a T3 thermal fault, which is a fairly high temperature thermal fault on that transformer. And that's what was driving it. So again, not a lot of hydrogen, so it didn't really identify partial discharge as a problem. The level of methane definitely indicated to me that there was some partial discharge there as well. But really from the overall diagnostic using the Duval triangle, basically it said it was more of a T3 thermal fault. And in this situation, basically it was due to a loose bottom terminal connection on that bushing is what was driving that. So good example of how you can utilize both the partial discharge monitoring and the DGA monitor in general, or in conjunction with one another, to identify what's going on. We talked about the increased fault activity and things like that. Monitoring the fault levels and the fault activity on your transformers can be a good idea. Putting this right in the transformer monitor is a good idea, because then it's going to follow the history of the transformer. It's not like your relays, which may change over time, and you've got to stave that value. In this case, the online monitor is basically tracking this over the entire life of the transformer. It's monitoring both the number of faults, the I squared T, the total accumulated fault current on that transformer, existing values, historical peak fault currents, and then basically a history of those faults and stuff like that. So, seeing this type of activity, both one, it can identify when we've got excessive fault activity, but it's also going to give us an indication as to the mechanical history that that transformer is experiencing. Again, with the renewables, I expect it to see probably be less. The magnitudes are probably going to be less, but the number of faults is going to probably increase in that situation. We talked about harmonics, basically, having some type of harmonic monitor on those transformers, and there's the inverter-based applications. is definitely a good idea. Based with our harmonic monitoring, we can identify not only is there a problem with the inverters, are they responding correctly? Are all three phases responding the same as we see system events? But also if there's filters that are present on the system, are the filters actually working? So again, it's going to provide us information not only, that maybe something's gone awry with the harmonic filtering that's in place, or even in the inverter itself, which can, help to identify. Again, it's just good information, providing real-time access to that info, and we can track it and basically provide guidance to the operators that something's going south on the system. So lastly, wanted to focus on basically a bushing monitoring case study, which I thought was interesting. This happened to be honest, that solar farm, that same load profile that we saw earlier, this happened to have OIP bushings, oil impregnated paper bushings. Now I know there's a lot of movement within the industry for, hey, the OIP bushings in the renewable applications seem to have issues. Let's go more to a dry type, the resin impregnated paper, resin impregnated synthetic. While those do perform better and they do provide a safer option, there's still, I think the verdict is still out as to, how the long-term performance of those is going to be with not only the expansion and contraction and things like that. There's some early indications that maybe that's causing some power factor changes in those bushings and stuff from that perspective. As you're doing that, basically you could also create some voids in the insulation, resulting in partial discharges. But we also have the harmonics, and what's the harmonic impact going to be on those dry type bushings as well that we need to be concerned about. So, but in this case, it was oil impregnated paper bushings. Here I've got both high side and low side monitoring. I can see on my high side, basically, I've got a very tight pattern. Basically, I'm running a sum of current method here. But you can see on the low side, basically, I've got almost a scatter plot. I see a lot of activity. Now, this isn't surprising when we saw the voltage fluctuations that we're seeing in the megawatt flow or megavar flow on the systems. So I think this is some of what's driving the activity on that bushing monitor right now. And what we can see is, high side is definitely doing good, but the low side is really hard to make a prediction as to which bushing is causing which bushing is having a problem, or is any bushing, or is this all just system related? So, as we looked at the data more, basically, I started looking at the individual leakage currents and leakage current angles, and what I saw again was large deviations due to system voltage fluctuations. In this case, basically, I've got a 30% deviation in bushing leakage current. Now, what I can see is basically it's affecting two phases. My center phase, basically bushing current 2 is much less. But all of that, could be driving imbalance currents and things like that and problems within the system. And how quickly these deviations occur, again, could be causing stress or putting stress on the equipment. This is that load profile we talked about before, the voltage fluctuations, all of which is driving some of that imbalance that we're seeing on the system. But again, it sort of made especially on the low side, it made us challenging to try to identify, do we have any bushing problems going on? This is just looking at the voltage profile a little bit differently. We can see again, it's pretty stable, but once we start generating, basically I start seeing increasing, and then when we're ramping it back down or bringing it back online, I start even seeing greater increases. So all of these voltage deviations that we're seeing, again, is driving maybe those spikes in the imbalance current, making it the data hard to understand, to identify if we have a bushing problem. There's also short-term things, as the inverters react to problems on the system. You're seeing fairly large deviations in voltage, very short-term and stuff as well. But one thing that's very interesting when we look at the data on the unit is basically there seems to be almost two different conditions here. Here's where we're generating. Not surprising, we see a lot of changes in phase angle, high spikes in imbalance current, and things like that. But then when we're offline, things are a little more stable. I'm seeing it both on the imbalance, on the phase angle, basically on two bushings, both on my B phase bushing, my phase 2 bushing, and on my phase 3 bushing. But again, it seems to be a load related, and then when we're not generating. So that prompted me to take a look at the data. Well, what if we start isolating data, looking at it basically in a loaded condition and in an unloaded condition? And when it's in the unloaded condition, which is what we're seeing here, This is more of what I would expect to see when I have a bushing degrading. For the most part, it's got a pattern, tends to follow, and I start seeing a few points that exceed my warning threshold here. And then sure enough, as I dig into that data more, OIP bushings, one of the biggest things that we see with OIP bushings is as they fail, they tend to get an increase in moisture ingress on the bushings. That increase in moisture ingress basically results in an increased temperature coefficient in the bushing. Basically, what I'm seeing is as the imbalance current changes, basically I'm seeing it's correlating with temperature. So when the temperature is low, my imbalance is low, but when my temperature is elevated, basically I see a higher imbalance. Reason being, power factor is heavily temperature dependent. And the more moisture you have in your insulation, the greater you have, basically the greater there's going to be a problem in there. And the monitor is detecting this and identifying this. In a previous presentation, one of the questions was, when can offline tests be misleading? If there's a lot of moisture in the insulation, power factor tests at lower temperatures actually can be very misleading. This graph shows it very, very well. At this point here, basically, if I'm testing with an offline test at this point, basically I'm not, my power factor is going to be down. And if I'm testing at an elevated temperature, when the transformer temperature is high, basically at this point, the power factor is going to be much, much higher. So that could be one indication. And we track that easily with the monitor, basically, when I look at that temperature coefficient curve. So in this situation, basically to get to the bottom of things, what was happening, basically we had to take a look at measurements, compare it at similar operating conditions, and we may have to do that same thing when it comes to some of the partial discharge activity and things like that to identify what's happening. But bottom line, the online monitoring systems, online monitoring makes this whole task easier, and it allows me the opportunity to identify these correlations. Excuse me. So in conclusion, basically inverter-based generation has fundamentally changed the operating environment for high voltage power equipment, not only for transformers, but also for breakers and for switchgear applications and things like that as well. Stressing insulation in ways that we never expected before. Rotating machines relied heavily on the inertia to keep the system stable. Inverter-based systems are reactionary. They rely on a rapid response of the inverters to compensate for system disturbances. When that happens, basically that can result in increased harmonics, switching transients, voltage frequency deviations, and things like that, because it's reacting to what's happening on the system. And when the problem goes away, it still needs time to basically turn that off. All of which can cause, again, voltage transients, frequency deviations on the system, and cause additional stress in our high voltage assets. Driving both thermal cycling, insulation degradation, as well as dielectric problems within the insulation. So the rapid response of these systems basically creates steep front waveforms, high rates of change in voltage and frequency, which again puts the insulation under constant attack. So, finally, continuous online monitoring has really become essential to detect these early stage failure modes, improving your situation awareness, making sure that we can bring those renewable assets online when we need them, and to make sure that they're going to stay online when we actually, when they are generating, and overall extend your asset life. So that's what I've got for you today.